Hello, I'm Manuel Bardiès, and in this webinar we're going to study the different steps from the activity measurement to the dosimetry report. My declaration of interest. Okay, so this figure represents what we call the clinical dosimetry workflow. That means the different steps that need to be made in sequence to go from the calibration to patient data acquisition, activity determination, registration, segmentation of images acquired at different time point, time activity curve, fitting and time integrated activity assessment, absorb those calculations, and then alternate additional calculation and presentation of the results. So as you can see, the clinical dosimetry workflow is a different sequence that are crossed to do clinical dosimetry. And obviously all these steps are different, but should be treated with the same care because the accuracy on the results is conditioned by the accuracy of every step of a clinical dosimetry workflow. So let's go through all of them. First of all is the calibration. It's an essential part of a procedure. It's obviously addressed by the physicist. It must be consistent with a clinical procedure. So, and that's the very first advice. I'm going to repeat it, but I would urge you to do the calibration in the very same protocol as the patient acquisition. There's always a possibility to correct, but it's not so easy, and it's a wonderful source of mistake. So we should try to be consistent between calibration and clinical acquisition. And in general, it's not standardized. And for example, what you derive and what the clinical dosimetry software are waiting for you to input, it can be count per megabecquerel, or it can be count per second per megabec, it can be megabec per count, etc., etc. So here again, you have to be very, very careful when you are input a calibration factor in a clinical dosimetry software. Calibrations. You've got calibration of a radionuclide calibrator to make sure that the activity administered to the patient is assessed with good enough accuracy. You've got gamma counters, for example, if you need to count activity in blood or urine that can be taken out of patient. And you've got obviously gamma camera. So we tend to think immediately of gamma camera and calibration of a gamma camera, but we also have to calibrate the two other devices. And it's interesting to notice that cross-calibration is essential. So do your calibration on the same day, if possible using the same sources on the different devices, and that will increase the degree of confidence you can have in the whole process. So how do you measure sensitivity? How many becquerel per count do you have? So there are two broad approaches. One is considering point sources in air, and the underlying hypothesis is I'm able to do all the other corrections. I'm able to implement, my software is able to implement, attenuation, scatter, PSF, etc. Everything can be corrected. So I just need a point source in air, and then I can manage the rest. The other approach, which I would say is probably more spread, is to use a phantom like, JSEC phantom, whatever, a water tank with homogeneous radioactivity distribution inside, and with a volume, if not a geometry, but at least a volume that looks like what you will have in real life with a patient. So then you have to correct for partial volume effect. So this is a description of the partial volume effect. You've seen that in the other webinars by Pablo Minguez-Gaviñas, so I'm not going to enter into the detail, but obviously you have to correct for partial volume effect, and this is how it's usually done, by using JSEC phantom with sources, spherical sources of different volume, and you're doing a recovery, contrast recovery curve with those sources of different volumes. And then comes the validation. So you've done the calibration of sensitivity or contrast recovery, and then you have to test that. And obviously to test that, you should use another phantom than the phantom that was used to assess the calibration. So you can have a variety of phantoms, well, not so many actually, but you have some that are adapted to validation. Some have got a variable density, like the one to your left. So you can see you've got lungs that have a density of lung, you've got a spine that is in Teflon, that has a density that is close to that of bone. And that to the right, the liquid fill has got, everything is plastic and water, so you will not really test your density correction on that phantom, but it's got volumes that have a realistic shape, like a liver, you've got a spleen, 2 kidneys, even tumors inside the liver, and so on. So you have to select a phantom that is adapted to your procedure or your clinical situation. Here's another example of a phantom that mimics patient geometry, but here again, it's only the region or the volume you are interested in. Here is the kidney, so you've got a phantom that is made with 3D printing, and it has cortex and medulla that you can feel independently. So that's a good phantom to test quantitative imaging of kidney, and obviously that's for PRRT with lutetium-177. So we have calibration acquisition, we have patient data acquisition. As I said, I will urge you to do the calibration and patient acquisition in the same way, because it's good for robustness, traceability, reproducibility. So design the same operating procedure for both calibration and patient data acquisition. Then, activity determination. That really depends on the type of acquisition. I would say that SPECT-CT is probably state-of-the-art these days, so try to avoid planar imaging, because it's difficult to have quantitative imaging with planar imaging. The question can be raised for hybrid. We will see later that you can have accurate results, but usually the same hybrid procedure where you have several planar associated to one SPECT-CT that is considered more quantitative, is highly variable from one center to another center. So it really depends. Your center, if you implement overcorrection, I would say you can have fairly accurate or good results with hybrid approaches. If you want to compare your results between two different centers because it's a multicentric trial, because you want to be able to compare your results with those obtained by other centers, I would advise to use SPECT-CT mostly. You can have vendor-based activity determination. You have now more and more modules that are quite expensive but are given by the manufacturer, or you can use reconstruction and corrections and quantification made on vendor-neutral software like those proposed by this producer. I must stress the importance of EARL, so for the accreditation for quantitative SPECT, as was done in the past for quantitative PET. So these are some papers to read. And then segmentation and registration. So I first state these two steps are not independent, which is why I put them in the same step in the clinical dosimetry workflow. So why is that? First of all, registration. Registration means realigning images acquired at different time points. So it can be manual, it can be rigid, it can be elastic. There are a variety of algorithms and possibilities or software for image registration. So obviously you have to test them, and it's not so easy to say how to validate registration. And then we have segmentation, and segmentation is just making sure that we delineate organs and tumors in the patient, and that can be manual, that can be semi-automatic, threshold-based, and now it can be made more and more often automatic thanks to artificial intelligence. So artificial intelligence is here, and it's a potential game changer, because this is normally a very long and tedious step, and that can be made automatic and very fast thanks to AI. So now how comes, and obviously the question is how to validate it, and how comes they are connected? And they are connected because usually what you're doing in clinical dosimetry, you're selecting one reference frame, and that reference frame is used to define all your volume of interest. And then these volumes of interest are propagated from one time point to the next using the registration that was done previously. So you have one reference image that is usually selected for both registration and segmentation, and that is being used for further steps. And obviously, the way you selection one reference instead of another can impact the output of dosimetry. So time activity curve fitting and integration. So I put that step here, assuming that you have activity in time, you have time activity curve fitting, and then you integrate that. So according to the mode formalism, it can be made, the fit can be done, and then integration can be done using trapeze or mono B multi-exponential. It's highly dependent on time sampling. Obviously, the best time sampling, the best the accumulated activity determination. I would like to drag your attention. I mean, you really have, in that example, you have 4 time points, which is not that bad. I mean, quite often we're very, very happy if we have 4 time points to sample the pharmacokinetic of a given patient. And then that defines 2 regions. One region between the first time point and the last time point, which I call interpolation, where it's fairly easy to get the time integral of activity. So that's the area under the curve. It's easy. You can get that with trapeze. It's easy and it's quite accurate. But then the issue is for all the region in orange, which is extrapolation. So between 0 and the first time point and after the last time point, everything you will obtain in terms of time integrated activity or cumulated activity will be extrapolated. So you really have to be careful, especially when the fraction of extrapolation becomes significant. If 40, 50, 60% of your time integrated activity is obtained from outside the time sampling, from the extrapolation, then you have a potential issue. It means that your time sampling is probably not optimal. And then the absorbed dose calculation. So I'm not going to go into much detail for all of those because you've seen them in different lectures and different webinars before. But then obviously it can be done, the absorbed dose calculation, at the organ level or at the voxel level. It may or may not implement radiation transport. You can have local energy deposition, for example. You have different algorithms. We've seen before that you have basically 3 types of algorithm, and you have different resources like Monte Carlo code and so on that can perform absorbed dose calculation. So this is just the algorithm for selecting the absorbed dose calculation algorithm. So you have questions, depending on the geometry and radiation characteristic, are we in a context of non-penetrating radiation? If yes, then local energy deposition is probably sufficient. If not, second question, are we in homogeneous medium? If yes, then convolution can be sufficient. If not, then you should better implement Monte Carlo. So these are the 3 types of algorithm. Again, they can be implemented in different clinical dosimetry software for model-based dosimetry, where you're going to use S-value that can be generated using those algorithms, or for image-based, organ voxel-based dosimetry. And then there's post-processing and reporting. So your calculation may not be finished or completed when you get the average absorbed dose. If you have a voxel-based calculation, you can have absorbed dose volume histogram. You may want to implement radiobiological variable like BED and other dosimetry-related indices like minimum absorbed dose, mean absorbed dose, median absorbed dose, maximum, and so on. So it may require extra calculation, and that depends obviously on the clinical endpoint. So when everything is said, it's a clinical demand. Say, I want to get those parameters because I want to put those parameters in front of the clinical outcome. toxicity or efficacy. So these are some examples provided by Marta Cremonesi of computation of BED, EUD, EUBED, and dose volume histogram, relying mostly on voxel-based dosimetry. And then reporting. So you have here an example provided by my colleague Laura Santoro from Montpellier. And in Montpellier, we are generating two reports. So to the right, and that's in French, but to the right, you have a report that is given to the clinician. So with patient name, with number of treatment, is it the first, second, third, fourth cycle of, that's for Lutathera therapy. And you've got the absorbed dose delivered to the organ at risk. So the kidney, right, left, the liver, and so on. Bone marrow using L2, L3, L4. And then the lesions. So a description of a lesion and the absorbed dose delivered to the lesion. And that's fine. That is what is given to the clinician. And then to the left, you've got the physicist report. And you've got much more information about calibration, how calibration was done, when it was done, the kind of fit, is it mono, bi-exponential, etc., the goodness of a fit. So all these informations that are important to ensure traceability and reproducibility. Everything should be documented, everything should be stored for every single patient. So I would stress that reporting is an integral part of the clinical dosimetry workflow, and it's very important to select, if you can, a software that actually does an automatic reporting of a procedure, because again, it decreases the chances of a mistake when you are just copying the results in a report. So, as we're reaching the end of that presentation, you have a clinical dosimetry workflow. It's done of different steps. What I have presented here is what I could call the conventional clinical dosimetry workflow with activity, registration, segmentation, time activity curve fitting, absorbed dose calculation, and results. There may be alternate clinical dosimetry workflow. For example, you may perform the absorbed dose rate calculation first and then integrate absorbed dose rate in time. So you can swap two of those steps here. There are clinical dosimetry workflow with or without registration, with segmentation being performed at every time point and so on. So this is just an example. And for every clinical situation, you may have alternate clinical dosimetry workflow. And obviously, all the steps need to be checked to get to have a correct